We now move into an evaluation of the chemistry of amines. So I want to start in this lesson by talking about nomenclature and basicity of amines. So when we name amines, we generally use common names, and the way the common names are constructed is you just generally list the substituents followed by the word amine. Okay, so some examples are on the screen here: ethylamine, isobutylamine, those are both primary amines. Ethylmethylamine, secondary. Diethylamine, another secondary. And then two tertiary amines, triethylamine and ethylmethylpropylamine. Okay, and recall from the beginning of organic chemistry that primary, secondary, and tertiary refer to how many alkyl substituents are directly bound to the nitrogen. It has a slightly different definition than primary, secondary, and tertiary with respect to alkyl halides or alcohols. Now, there are several aromatic amines that I think it's actually important that you know the structure of. And you have met all of these at least a little bit earlier in your study of organic chemistry. But when you have a benzene ring with an NH2 sticking off of it, that's called aniline. The 5-membered aromatic amine with a nitrogen in the ring is called pyrrole. The 5-membered ring amine with 2 nitrogens in the ring is called imidazole. Then when you have this 5-6 ring system, so a benzene next to a pyrrole basically, that is called indole. Indole is found in the amino acid tryptophan. Imidazole, by the way, is found in the amino acid histidine. And then finally, pyridine is the 6-membered ring similar to benzene, but instead of one of the carbons, you have a nitrogen in the ring itself. So the most important property of an amine is that they are basic. And I am showing here the acid-base chemistry. So if we take an amine and react it with hydrochloric acid, the lone pair picks up a hydrogen and you make the protonated amine. Okay, so amines are not as basic as hydroxide, but they are stronger bases than either acetate ion or water. And of course, you need to look at the pKa of the conjugate acid in order to be able to compare basicity. So remember the acid-base equilibria that are involved. You have the protonated amine being in equilibrium with the neutral amine, the protonated amine, of course, being the acid, the neutral amine being the base. And then you have the definition of the Ka, and then the pKa, of course, is equal to the negative log of the Ka. And just because we usually think in terms of acids when we think about pKa, I want to remind you explicitly that a more basic amine has a conjugate acid with a higher pKa. So if the conjugate acid is weaker, the base is stronger. Okay, so let's look at some data. So I've given you 5 amines here: ammonia, triethylamine, aniline, pyridine, and an amide. It could be any amide. So ammonia and triethylamine have very similar basicities. Their conjugate acid pKa is in the 9 to 10 range. We could go into more detail about why triethylamine is slightly more basic than ammonia is. I'm actually not going to in this lesson. But what I would like us to understand is especially what is going on with aniline, and then by extension, what's happening with pyridine is somewhat of the same idea. And then finally, why amides are really so different from amines. Okay, so let's try to understand this data. So just like acids are stronger acids if the negative charge left behind after a proton is removed is stabilized, amines are weaker bases if their lone pair is somehow stabilized. So aromatic amines, looking at aniline here, are actually less basic because of delocalization of the lone pair electrons by resonance. Okay, so of course we have structures 1 and 2 here, which are simply the 2 Kekule structures for aniline. But beyond that, I can draw structures 3, 4, and 5, where I take the lone pair electrons from the nitrogen, use them to form a carbon-nitrogen double bond. And then what that's going to do is actually put a negative charge onto either the ortho in structures 3 or 5, or the para in the case of structure 4, carbons of the benzene ring. Now, you're not gonna like these structures, I know, believe me. I don't like them either, but they help to explain the reactivity. Okay, they are minor resonance contributors, but the fact that they are there at all, which is not true for an alkylamine, explains the fact that the nitrogen is less basic. Because of course, in the structures where the nitrogen bears a positive charge, it is not basic at all. Furthermore, if the aromatic ring contains a substituent that can further stabilize the electron density on the lone pair by the addition of another resonance structure, the amine is even less basic. Okay, so if we look at para-nitroaniline and look at structure 4, what's drawn on the left here is structure 4 for para-nitroaniline, we can add one more resonance structure where we stick the negative charge onto one of the oxygens of the nitro group instead of the carbon of the aromatic ring, and that makes para-nitroaniline an even weaker base because its lone pair is more delocalized by resonance. We can do the same thing actually with orthonitroaniline because we have a structure equivalent to structure 3 in which we have the minus charge in the ortho position to the NH2. And we can also get another resonance structure where we delocalize this minus charge onto one of the oxygens bound to nitrogen. Okay, so with what we call an electron withdrawing group in the ortho or para position, you can get these additional resonance structures. So it's not just nitro groups, it's carbonyl groups, it's nitriles. So if you look at this data, aniline, of course, has a pKa of 4.6. If you put an electron withdrawing group onto the aniline, the pKa of the conjugate acid drops all the way to 1.7. That is a stronger conjugate acid, which means we have a weaker base. And contrary-wise, if you put an electron donating group, such as a methoxy group, into the para position or the ortho position, those electron donating groups are going to actually donate electron density into the ring and make the nitrogen more basic, so the pKa of the conjugate acid is a little bit higher in this case. Although notice the effect is much less pronounced. Difference between 4.6 and 5.3 is only 0.7 pKa units instead of a difference of 3 pKa units when you put on an electron withdrawing group. And I will leave it up to you as an exercise to actually draw the resonance structures that you get with the methoxy substituent. Okay, so then the last thing we have to consider are amides. And as you saw from the data, amides are much less basic than amines, and they have a pKa of around 0. And the way to understand this is that an amide itself, the neutral amide, we can actually draw 3 resonance structures for it. And we did something similar to this for esters also. This explains also why amides are less reactive towards acyl transfer reactions than other carboxylic acid derivatives. So you have the neutral structure on the left, you have the center structure in which you have the positive charge on the carbonyl carbon and the negative charge on the carbonyl oxygen that we have seen before as explaining the carbonyl reactivity, why the carbon is electrophilic. But then we have one more resonance structure available to the amide where you take the lone pair on the nitrogen and use it to form a carbon-nitrogen double bond. And this is a particularly good structure because in this one, all of the electrons are obeying the octet rule. Now granted, both of these structures have separation of charge, but this third structure is better than the middle structure. And once again, in this third structure, the nitrogen does not have a lone pair on it anymore. It has a positive charge, so it is not basic at all. If you protonate the amide, then you cannot make this third resonance structure because there is no lone pair left on that nitrogen. It has already been used up in the protonation. So then you only get that second resonance structure, and that's now a particularly poor resonance structure because you have two positive charges right next to each other. So in this case, we say that the protonated amide really does not have any resonance stabilization, whereas the amide itself, not protonated, does have resonance stabilization. So the loss of that resonance stabilization upon protonation means that this nitrogen actually does not want to be basic, and thus its conjugate acid is a strong acid. Okay, so that's our overview of the basicity of amines, and then in the next lesson we're going to look at some more examples of important naturally occurring amines called the alkaloids.